Hello, everyone. We'll continue shortly with 11.4. We'll finish that section. A few of you asked about the homework, and there was some problem with my MATLAB, but I extended the deadline till a couple of more days, April 3rd, in case you couldn't finish up with that assignment. So just make sure you do it on time now. I also, before we started the class, wanted to, I see as some of you are putting your names in the chat. That's great. Please do so if you haven't done it yet. And also, I wanted to let you know about our exam. So the class, our next exam, it has already been decided by the course coordinator. All of us 150B instructors are going to be doing it the same way. So our exam is going to be through Canvas. It will be posted. You will have 24 hours to do it. And I will provide instructions on Canvas on how to upload your exam. So you're supposed to download it, print it, solve it with by hand. So it has to be your handwriting, and then upload it. And then there will be a rubric there, and it will be graded there. So you will be able to see how your exam is graded as well when it is done. So again, I want to ask you to be patient, because this is probably going to be taking more time. Does it need to be submitted as a PDF? There's several choices. It could be a PDF, or it could be that you take pictures even with your phone and you upload it page by page. You can upload several files. I will provide instructions, so it's not gonna be a big deal for you guys. It's actually should be pretty straightforward. All right. Okay. Questions about that? Any other questions about our upcoming exam? Oh, we so the day. The date of the test, so we're keeping more or less with the schedule. We're a little bit behind because of the class that we canceled, but we're slowly catching up. So we're still gonna have a review like we usually do, and we'll go through the sample final questions for that particular, for the sections that are covered on the exam. But also the date where we're supposed to have the exam, we're still going to have class here. All right, we'll still use it either if we need to catch up because of the class we cancel, or as extra review. So even so, the exam is not going to be at the exact time for the class, because you have 24 hours. So that date, that particular date for the exam, we're still meeting here, and we're still having review. You can ask questions. You can maybe show me your work, or your work on the problems, or ask about specific ones. Okay, so just to let you know about that. Okay, so we'll continue with 11.4. So we were seeing how we could use these use new concepts that we learned, power series, Taylor series, how we could use those to solve other problems. So we did limits last time. We also did a particular differential equation, and today we're going to do a couple of other things that are still pending. So let me switch to the page and we'll get it started. All right, so here's what we're going to start with. We're going to start with example 5. So this is 11.4, example 5. And what it says is the following. It says, approximate the value of the integral it's a definite interval, 0 to 1 e to the negative x squared dx, with an error less than 5 times 10 to the negative 4. So tiny error. Oh, this is too bright. Better. Okay. So we need to approximate this integral. And see, here's the issue, guys. This integral over here, it's an integral of, it's one of those integrals that we cannot solve in terms of elementary functions. So if you're thinking, oh, I can do this integral, my correct way to do this would be that I simply try to, you know, find out this antiderivative, all right? That would be really, really hard, actually impossible. So it can be shown, it has been shown before, that this particular function cannot be, so the antiderivative of this function is not among those that you can create with elementary functions and the operations we know, right? So it's, you cannot do inverse tangent or inverse sine on any combination of those functions that we know that will give you this antiderivative. Yet this expression actually happens, and it appears all the time in statistics, for example. So it is important to be able to do integrals like this. And in this class, we haven't done a lot of these. You know, it's called numerical integration. How to, even if you cannot calculate this integral directly, you can still approximate it to any degree of precision that you want. So this is an example of that, how we can solve this integral in a different way. And what is that way? Well, the way is to consider the Taylor series of e to the y, e to the x. So I'm going to write y because I'm going to do a substitution. You sort of are anticipating that already, I think. So here's a power series for e to the y. It's one of those that you should already start memorizing. And this is good between negative infinity and infinity. Right, so it works for every real number. And so the idea is to use this to integrate these, because we can integrate a power series term by term. It was one of our earlier theorems, and we used it to actually come up with new power series, if you remember about that. So here what we can do is first plug in what we want, which is set y equals negative x squared, because that's the function that we want, right? And then when we do that, we get our expression for e to the negative x squared. E to the negative x squared is going to be, it will be the series from 0 to infinity, negative x squared to the k over k factorial, which we can rewrite as negative 1 to the k x to the power 2k over k factorial. All right, and because this one is good for any y between negative infinity and infinity, then this one will work also for any x squared. So this is good for any x between negative infinity and infinity. And we actually only need it between 0 and 1, right? Because that's the integral we want to do. But it doesn't matter. It works for any x. All right? So all we need to do now is to integrate it. And it's actually not a difficult integral when you have it as a series, because all you need to do is integrate easy things like x, x squared, x cubed, x to the fourth, which we know how to do, right? They're straightforward polynomials. So here we go. We want to integrate from 0 to 1 e to the negative x squared. And to do that, what we need to do is integrate this power series from 0 to 1. Now, it looks scary because the expression has the integral and the sigma for the sum, but it's actually nothing extraordinarily difficult. It's actually pretty straightforward. And here's where we use the fact that we can integrate this by integrating term by term. In other words, we are allowed to switch these two operators. So we can do this sum, the series from 0 to infinity of the integral from 0 to 1, negative 1 to the k, k factorial, x to the 2k dx. There's a dx missing over here. Let me put it right here. All right. So all I need to do now is to do this integral. And as I was telling you, this is a straightforward integral because this part over here is just a constant, right? This is constant. So we should not worry about that part. So we can now integrate. It will be the series from 0 to infinity. And this is a constant, like we said. So just rewrite it again. And then we integrate x to the 2k. X to the 2k. And the way we do it is we add 1 to the exponent. And we divide by that new exponent. And this is a definite integral, so we're evaluating this from 0 to 1. Okay, so now let's do the evaluation. So I still need to write down the series, which is what I'm doing right now. And then right here, you plug 1. So it's going to be 1 over 2k plus 1. Minus, you plug 0, so it's 0 over 2k plus 1. And then we simplify this. I mean, this is obviously 0 goes away. So our integral, let me write it here, that we're looking for. We just solve the integral, believe it or not. I mean, the answer is not an easy number, right? The answer is in terms of a series. This series. All right. So that's if you were asked to do the exact value of the integral, this would be the answer. This is the exact value of this integral over here. Now, in this particular problem, we're asked to approximate, right? And the way we approximate is by taking some of these terms. So let's write the first few terms here, and then we'll talk a little bit. I mean, how many should we use to get an appropriate approximation, depending on the degree of precision that we want. So let's write the first few terms here. When k is 0, this is -1 to the 0, that's 1. 0 factorial is 1, and 2 times 0 plus 1 is 1. So the first term is 1. Then k is 1, it will be minus, thanks to this -1 to the k. Then is 1 factorial, which is 1. And then 2 times 1 plus 1, that's 3. Next term, it will be positive 1. Then 2 factorial, that's 2. And then 2 times 2 plus 1, that's 5. So 2 times 5. Then next one will be positive 1. Now we're doing when 0, 1, 2, 0, 1, 2, 3. Okay, so this should be minus, my bad. Minus, when it's 3, then it's 3 factorial is 6. 2 times 3 plus 1, that's 7. Right? And then we continue like this. Maybe let's do a couple more. So the next one will be positive when we have 4 factorial, that's 24, and 2 times 4 plus 1, that's 9. And one more, minus 1 over 5 factorial times 11, and 5 factorial is 120. Right? So let me rewrite it here. So it's 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 24 times 9, which is, what is 6, 3, 216. And then minus 1 over 5 factorial is 120, and 120 times 11, whatever that is. In fact, let's just leave it like that. 5 factorial times 11. And then there's more terms, of course, right? Okay. Now, you could evaluate this quantity, 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 2. And every time you get a better and better approximation. Now, you may be wondering, well, how do I know where to stop, right? How do I know what is the degree of precision? And to answer that, what you need to remember is that this is one of these alternating series, right? That goes back and forth, back and forth, back and forth. So let me make a picture here for you. So this is what we're doing. We started at 0, and we first are jumping forward 1. Then we're jumping backwards 1/3. Right, this is 1/3, so now we're at 2/3. Then we're jumping forwards 1/10. And then backwards 1/42. And so on, right? So because every new jump is smaller than the next one, then the error in the approximation, so the true value is somewhere over here, right? Somewhere over there. And its true value is always less than the next jump. So we learned that when we talked about alternating series. So the error is less than the next jump, right? So right now, how many did we do? We did 1K is 0, 1, 2, 3, 4, and 5. So then with this one that we did, the error is less than the 6th jump. So in this case, the error is less than, what is the 6th jump? The 6th jump is 1/6 factorial, 2 times 6 plus 1. And 6 factorial is 720. And this is 13. Right? So this number is about 0.000107 according to the book. All right? So the error is less than this, and this satisfies what we wanted. So the problem asks to get an error less than 5 times 10 to the negative 4. Right? Now the question here is, well, what if this, you sort of guessed it, Professor. How do you know to stop at 5? Well, yes, I was just sort of trying the first few. Well, let's suppose that this number is not good enough. What do? Well, I keep going, right? I do another term. And if we use more terms, so if we use 6 terms, the error would be less than, well, the next term, which is 7 factorial times 7 plus 1. And this is now 1/5040 times 15. An even smaller number than this, right? So, in fact, let me tell you right now more or less what that number is. Okay, this is about 0.00001322 75. Right? So you see way more. So now these first 4 digits are correct. Over here it was 3 and maybe the 4th one. Here for sure 4 and maybe the 5th one, right? And so on. So let's say you don't like this. You want even more accuracy. Well, use more terms, right? It's as easy as that. Okay? All right. So be aware. I remember last final exam, we actually had a problem like this in the final exam, where they didn't ask for the approximation, but they asked for the exact answer to the integral. So this series as the answer for the overall integral. All right. Okay. So this is the end of this one. I wanted to do another one. So let's go to example 6. All right, example 6. It says use the Maclaurin series for inverse tangent. It has 2 parts. Part A, use the Maclaurin series for inverse tangent to evaluate 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 plus 1/11, etc. Right? We see the pattern. It's just we're alternating and we're going through the reciprocals of the odd numbers. All right. How do we do this? Well, let's start with the Maclaurin series for inverse tangent. And if you remember, We got that one by taking the 1 for 1 over 1 plus x squared and integrating. We did that a few days ago. So here is the one. So inverse tangent, this time I'm going to write arctangent, is the following power series. It is from 0 to infinity, -1 to the k, x to the k, over 2k plus 1. And this is the interval of convergence. We got it before. The interval of convergence is from -1, not including -1, to 1, including 1. All right? Okay, so this problem is easy, right? All we need to do to figure out this one is see how they are related. How can we get this one, the one in purple, from the one here, right? What x should we use? What x should I plug here, which belongs to the interval of convergence? That's important, so that we get this one here. And which one should that be? That's right, Ben and Michael. We just plug 1, right? It's as easy as plugging 1. If we plug 1, well, we get 1 to the k is exactly what we want. It will be the series that we want, just -1 to the k over 2k plus 1. So this beautiful 1, 1 minus a third plus 1/5 minus a 7, etc. And what is it equal to? Well, arctangent of 1, right? And what is arctangent of 1? Anyone? Yes, pi over 4, right? Because the tangent of 45 degrees, or pi over 4, is 1. So this one is pi over 4. And again, that's a beautiful expression, right? Again, one of those that if you didn't know any better, you wouldn't believe it. How can something like pi has to do with something like straightforward as the odd numbers, 1, 3, 5? So this is the pretty expression we just deduced, that pi over 4 is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11, etc. Right? And by the way, if you've ever wondered how they figured out what are the digits of pi, well, you could do them with this one, right? You could approximate pi, or pi over 4 in this case, to any degree of precision by calculating a lot of the terms in this series, right? It turns out that this particular one is actually not a good one to use because it converges slowly. But there are other ones that are converging quickly, and those are the ones that are used to calculate pi to millions and millions of decimal places, okay? But pretty identity, no doubt. Let's take a look at part B now. So part B asks, part B, let f of x be equal to e to the x minus 1 over x, for x different from 0, and f of 0 is 1. Use the Maclaurin series for f to evaluate f prime of 1. To evaluate f of 1, f prime of 1, the derivative at 1, and the series from 1 to infinity of k over k plus 1 factorial. All right, so let's start first by figuring out what is that power series. What is the power series, the Maclaurin series, for e to the x minus 1? Okay, and as usual, we start first with the one for e to the x. So what is the power series for e to the x? And again, that one is one that appears very, very often, so you would be wise to learn it. It's x to the k over k factorial. And this is good for every x. It's one of the better ones because it works regardless of what the value is. All right? Okay, so now that's not the function we want. Let me show you. The function we want is actually e to the x minus 1 divided by x. So let's do that one. So let me write it in a more, I'm going to write the first few terms. So the first term is 1, then it's x, then it's x squared over 2 factorial, x cubed over 3 factorial, x to the 4 over 4 factorial, etc. So if I want to do e to the x minus 1 over x, all I gotta do is subtract 1 and then divide by x. So it will be x plus x squared over 2 factorial plus x cubed over 3 factorial, etc. divided by x, right? And all I need to do is, well, simplify each one of the fractions. So it is going to be 1 plus x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial, etc. Right? Now let's write it back as a series. How can I write this series in sigma notation? Well, it's kind of like this, is x to the k, as usual, and then we're dividing by k plus 1 factorial, right? So this time, if it says 2, the number on the bottom is 1 more. If it says 3, the number of the bottom is 1 more, and so on, right? And starting at 0, going all the way to infinity, right? Okay, so that was our first request, to get the Maclaurin series for this one, and to use it to get f prime of 1. So instead of doing the derivative of this function, which seems complicated, right? What we're going to do is we're going to take the derivative on the right-hand side. So here we go. If you want to take the derivative of this, well, that's the same as taking the derivative of the series. Right? And how do we do the derivative of the series? Well, we can take the derivative of each piece. Correct? Now, this k plus 1 factorial is just a constant, so we can take that out of the derivative. So all I need to do is do the derivative of x to the k. And that's easy, right? It's k x to the k minus 1. And the first term, 1, the derivative of 1 is 0. So we can start this at 1. All right? So that's a derivative. And we wanted the derivative at 1, right? So we wanted f prime of 1. So that's this derivative when x is equal 1. So all I need to do is plug 1 in here. And when I plug 1 in here, I get k over k plus 1 factorial. Right? Okay. All right. Which was actually part of the question. Let's go back to what the question asked us. The question asked, so use the Maclaurin series to evaluate f prime of 1 and also to evaluate this. Right? So now here's the beauty thing. So we know that the derivative of 1 is this series. But we did it kind of like the hard way, right? We did it with the series. There was no need to do it that way. We could have just taken the derivative of this the usual way and then just plug 1. So now let's do that so we know what the answer to this series is. So let's figure out what is the derivative of this the regular way. We use the quotient rule. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the square of the denominator, and we gotta plug 1. So this is the derivative of e to the x is e to the x times x minus e to the x minus 1 times the derivative of x, which is 1, divided by x squared. and we want when x equals 1. So let's simplify. That is x e to the x minus e to the x plus 1 divided by x squared when we plug 1. And now let's plug 1. So this will be 1e minus e plus 1 over 1. So the e's go away. And the answer is 1. So believe it or not, in a very quick and smart way, we just showed that this series, k over k plus 1 factorial, actually equals 1. Nice, right? It's like an indirect way of figuring things out. All right. Okay, so that's essentially it for this section. There is another example, example 7, which is nice, but I'm going to, there's still a couple of examples actually. So they're not as relevant, and I want to get, in fact, never mind. Let me do one more. Let me do example 7, which I think is still important. And then we'll start the next section. So here's example 7. Example 7, it says, identify this series. And here is the series. It's 1 minus 2x to the k over k factorial. And give its interval of convergence. All right. So this is kind of one of those problems where I show you a series and you gotta see if you can come up with the expression, the formula for that series. And we'll try some that are, you know, we know how to do it the other way around, right? If I first show you the function, if you want to do the series, you can do the Taylor series, right? You can find the derivative, the first derivative, the second, the third, and plug the center that you want, and that way you get the power series. So this is kind of like the reverse question. So I show you the series and I ask you what would be the formula. All right, so what is this one related to? Well, it kind of looks like the e to the something, right? So let's write that one here, e to the y. What is that one? That's y to the k over k factorial, right? And we know this one is good for any y. So how are these two related? What y can I use so that this one on top resembles the one in the bottom, right? That's the question you should ask. And here is easy, right? What is the y we should plug?
1 minus 2x.
Yes, exactly. 1 minus 2x, right? We put 1 minus 2x, and we get exactly the one we want. So we get, so then that means that that one is equal to e to the 1 minus 2x. And what would be the interval of convergence? Well, remember, this one was good for any y. So then if you plug what y stands here over here, you're gonna see that, you know, when you add 1, nothing happens. So this will give you that this is good between negative infinity and infinity as well, right? In other words, here you can put any y that you want. Therefore, here you can put any x that you want, and the convergence will be there as well. All right? So that's it. It was actually quite simple. So let's do something a bit more complicated. See if we can figure it out. So this is, I said I didn't want to do it, but it's such a pretty problem that I can't skip it. So similar question. So now we're given this one is -1 to the k, 4 to the k, x to the 2k. But now it looks more complicated, right? And the question is the same. Is what is the function? What is its interval of convergence? So find its interval of convergence and determine the function it represents. Now, a little caveat about this one. This is in generally hard, right? I mean, to, figure out what is the function of a given power series could be hard, or sometimes not. I mean, I can show you some series that you cannot figure out what the function I mean, sometimes there is not a specific explicit function that gives you the power series, right? Okay, but in this case, we can actually figure it out. So the first thing we should sort of realize is that this is sort of, see, we have the power 2 to the k, right? So maybe the first simplification we can do is, instead of using x, we can use x squared, right? Kind of like a little substitution of sorts, right? And in fact, this 4 to the k as well. So here's the first simplification we can do. Let's see if you agree. So you can rewrite this, keeping the things that, so the k, I cannot do anything about it. But all the other things, it's to the power k, to the power k, and to the power k. So I want to combine all of that, all right? So I want to put them all together, and it will be -1, the x squared, and the 4. And all of them to the k, right? Is that clear that these two are the same? I only factored everything that has a k exponent, and I put it together into one big umbrella, right? Like one big power series there. And here's why I want to do that. Because well, if I set this as y, so if I set y as -x²/4, then my new power series actually doesn't look as bad anymore. It looks like k y to the k. See, that's not too bad, right? That is not as challenging as we would think, right? Okay, now what else can I do? Well, the next thing that I can do is think about how you get something like this. When is it that you get something that looks like k y to the k? What does this remind you of? And to me, it reminds me of the derivative of y to the k, right? What's the derivative of y to the k? The k comes down, so it's k y to the k minus 1. That's the only problem, right? That I don't have the k minus 1, right? But maybe I can put it up like that, right? So what if this was like this? What if I write it as k minus 1 plus 1? And then I separate it into two parts. So one of them is k minus 1 times y to the k, and the other is simply 1 times y to the k. Right? And see, this is good because now this looks like the derivative of something, right? Now this first part looks like the derivative of y to the k. And this part looks like the geometric series, which we already know. So I think we're in the right track. We're on the track to figure out what this expression is. So let's see. So what is this one over here? Like we said, this first part looks like the derivative of y to the k. y to the k minus, hold on a second, there's something weird here. Let's see. What I wanted, I did it wrong, right? There's something weird here. So I should have, let's see, what is it that I want? I want the exponent. Okay, so so if I take the derivative of y to the fifth, is 5y to the fourth. So this number should be one more than this one. And I kind of did it the other way around, right? See, a little typo here. So I wanted this number to be one more than that. So should be over here plus 1 and here minus 1. It's what I wanted, right? So I want this to be one more. And this minus. All right, now it looks correct. So now this is like the derivative of y to the k plus 1, right? The k plus 1 comes down, and you subtract 1 to the exponent. And this one is simply y to the k. Okay, this was just an aside to fix my little mistake. All right, you with me so far? So let me backtrack a little bit. What is it that we're doing? We started with this one that looks difficult. And we're trying to make it simpler, right? So first step was we sort of put together everything that has a k inside, and we set y to be that. And that already simplified it a lot. Now it looks easier, right? It looks like this, k, y to the k. Now, next step is this reminded us of the derivative, but to be the derivative, this number has to be one more than the exponent. So to create that, I put the k plus 1 that I need, and then a minus 1, and separated this expression. So now it has the k plus 1, which is what I want, and then a minus, which is fine because that will be the geometric series. Then you realize this is the derivative of this one, and this is just the regular power series of the geometric function, right? So now, this derivative we can take out. So this is just now the derivative of this power series from 1 to infinity of y to the k plus 1. And this is just y to the k. All right? Now, we're almost done. We only need to replace these ones by the ones we know. I mean, we would like to replace this one with the geometric series, but there's a little problem because the geometric series starts at 0. Same for this one, right? For this one, maybe we should first do like a j substitution. So for this one, let's do j equals k plus 1. And so in that way, we get that this is the derivative of y to the j, and this, when k is 1, j is 2. So this one starts at 2. And this one is almost the geometric series, but it's starting at 1, right? So how to fix that? Well, easy. All we need to do is add the terms we want and subtract them, right? So here we go. So I'm gonna do it like I wanted it, starting at 0. But that means I gotta subtract the terms that I don't have here. And the terms that I don't have are when j is 0 and when j is 1. Same thing here. I wanna write the one that starts from 0 to infinity. But I have to subtract the term that I don't have, and the term that I don't have is 0 when k is 0. So that's y to the 0 is 1. All right? Almost done, because now we know what this one is. This one is 1 over 1 minus y. And we also know what this one is. This one is 1 over 1 minus y, right? So we're about to discover what, and we also know when we can do this. This is convergent. So this happens when -1 less than y less than 1. When that happens, we can replace this by the geometric series. All right? So we're almost done here because this is going to be the derivative of 1 over 1 minus y minus 1 minus y minus 1 over 1 minus y minus 1. And this is good if y is between -1 and 1. Now let's do the derivatives. This is like 1 minus y to the negative 1. So the derivative is minus 1 minus y to the negative 2 times the derivative of negative y, that's negative 1, minus the derivative of 1, that's 0, minus the derivative of y, that's minus 1, minus 1 over 1 minus y plus 1. All right, so this go away. And this minus times minus becomes a plus. So it's 1 over 1 minus y squared minus 1 over 1 minus y. Right? And if you want, you can put a common denominator here. Maybe we should do it. So it's 1 minus y squared. 1 minus, and this times that is another 1 minus y. So it should be 1 minus y here. And when we simplify, 1 minus negative 1 is 1 minus 1 is 0, and this is positive y. So this is y over 1 minus y squared. All right. And here's where it works, between negative 1 and 1. But now, remember, we use y to simplify it. Actually, we go back. What is y equal to? Here, right here. Y equals negative x squared over 4. So our last step is to set y equal to that and see what is our expression. So over here, recall that y is negative x squared over 4. So this becomes negative x squared over 4 over 1 minus negative x squared over 4 becomes positive x squared over 4 squared. And that's it. You can simplify a little bit if you want. Put the 4 on the bottom here. This is 1 plus x squared over 4 squared. And even maybe put the 4 inside if you want or not. So this is actually negative 4x squared over 4 plus x squared, everything squared. Okay. That's if I multiply top and bottom by 4, and then that 16 I put inside the square as a 4, and then the 4, and then 4 times x squared over 4 is just x squared, right? That's what you do from here to here. It's a simple simplification, but you can leave it here. That's fine. All right, and so that's the answer. That's our mysterious function. This power series that we started with is actually equal to this function. And where is it equal to this? Well, we said that for y between negative 1 and 1. So now we simply should plug what y stands for. So this is good for negative 1 less than negative x squared over 4 less than 1. And if we multiply by negative 1, this is 0 greater than x squared over 4. Greater than negative 1. Hold on a second. Am I doing things here? 1, not 0, 1. Greater than negative 1. All right, so this one is obviously worthless because a positive number is always bigger than negative 1, but this one is important, x squared over 4 less than 1. So this tells me that 4 is bigger than x squared, which tells me that x is between negative 2 and 2. So the radius of convergence is from negative 2 to 2, right? And just to summarize, the series that we started with from 1 to infinity, negative 1 to the k, x to the 2k, over 4 to the k, I'm missing a k, scroll on, is equal to negative 4x squared over 4 plus x squared quantity squared. All right, that's it. I know this is a difficult problem because it requires you to be creative, right? I mean, there's no, and like I said, there's no way we could do this for an arbitrary power series that I throw at you. But just come up with one at random. chances are you wouldn't be able to do this to figure out what is the function that created that one. So in this case, it worked because it had a very nice form, so to speak. All right? Good. So that's the end of chapter 11. And we're going to start a new chapter. And this also gives you a chance to have a little bit of a new start. Okay, this chapter 12 is meant to be an introduction. So the rest of the semester, as a matter of fact, is meant to be an introduction to multivariable calculus. So to 250. Even if you don't need to take 250, it's meant that way. So it's like the beginning of multivariable calculus. And at the beginning, it actually has material that is different, that is not dependent on the previous stuff. So again, it's a chance to get a brand new start, okay, and get the benefit of that. And our first subject there is going to be parametric equations, right? So chapter 12 starts with parametric equations. Okay, and here's the difference. The main difference is that I'm going to show you the difference between regular equations and parametric equations. Okay, so a regular equation, so regular equation looks kind of like this, like, well, y equals x squared minus x, for example, right? And we know this one. This is just a parabola. It's actually the parabola that goes through 0 and 1, like this. And the idea is that every point here, so you give me an x and I can figure out the y, and I figure the y by using this expression, right? So for every x, there is a y. So we have something that y is a function of x. So for every x, there is a y. For parametric equations, what we're gonna have is the following. We're gonna have this time, think of it this way. Think of a new variable, which is gonna be t. And I like to think of t as time, right? And then instead of having one equation, you're gonna have two equations, one for x and one for y. So it will look probably, to make one that looks almost like this one, it will be like this. You assign a parameter to x, say x is t, and then you assign one for y. Y is t squared minus t. So look, now we have two equations. So one for t, one for x, and another one for y, right? And t varies. The variable is now t. So for every t, there is one x and one y. And you can think that for every t, you get a x coordinate and a y coordinate. And that describes, say, the position of some object at time t. You know where it is at a particular time. And that's kind of nice because it's the difference between, I like to think of as the difference between having a static picture, right, of something that is just fixed, and a movie, right? In a movie, you get to see what happens as time goes by, right? So as time goes by, we get to see what is the evolution of whatever my curve is doing, all right? So let me show a page from the book related to this. Where is the book? Right here. All right, so here is what we're saying right here. So for parametric equations, we have x equals f and y equals g. And a and t ranges from a time a to a time b. Think of it that way, right? And here's a diagram that shows the difference between the two ways of thinking. So in a regular equation, you have x and a function, and then you get y equals capital F of x. In a parametric setting, you have both x and y, and you have two functions, the f function and the g function. And the variable is t, right? For every time t, you get an x coordinate and you get a y coordinate, right? So, okay, so let's do this example. It says graph and analyze the parametric equations. Okay, so how do we analyze it? Well, the idea is that for every time, so let's start with t equals 0. So when t is 0, what is x and what is y? Well, x will be f of 0, which is 0, and y will be g of 0, which is -4, right? So if I were to do a picture, this entire thing starts from x is 0 and y equals -4. So the point 0, -4. Now, as the time moves on, so as t goes from 0 to 8, see what's happening. The x coordinate is advancing in this direction, in the x direction, at 2 times t. So t equals 1. After 1 second, let's say that t is measured in seconds, the x will be 2. So x is going to be somewhere here in 2. So if we do t equals 1, the x will be f of 1, and that's 2. And the y would be g of 1, which is 1/2 of 1 minus 4. So that's -3.5. So after 1 second, we are in 2, and then -3.5, somewhere over here. So 2, -3.5, right? And okay, right now I'm just showing you snapshots, right? What happens at 0 seconds, at 1 second, and 2 seconds, and so on, right? I'm gonna turn back to the book again, so there's a better drawing there, so you can appreciate what's happening here. Right here. Yes, so this picture over here. So as you can tell, it starts right here at 0, -4, then goes, we did this to at time equals 1, would be this one, then time equals 2, 3, 4, 5, 6, 7, 8, etc. It follows this curve. It follows this curve that starts here and finishes here, right? Now, sometimes, like in this case, we can eliminate the parameter to figure out what kind of equation we have. So this curve over here, what is that? What curve is this? And in this case, it is possible to eliminate the parameter, but that's not always the case. So sometimes we can eliminate the parameter, and the way to do it is to solve for the parameter and plug it so that you eliminate it. All right, I'll show it to you with this particular example. Here's how we can eliminate the parameter. We can eliminate the parameter by solving for it. And plugging. And the problem is that sometimes solving is very difficult, right? In this case, it's not, because we can start with the x equation and solve for t. So t will be x over 2. And then plug into the other one. So then y will be 1/2 t squared minus 4. But t is x over 2, so we get x over 2 squared minus 4. And this is x squared over 8 minus 4. And now we recognize this as a parabola, right? It's a parabola, and now we know that this curve is actually a piece of parabola. From this point, from the point 0, -4, to this point, which I didn't calculate it, but it's 16,28, there, based on the page from your book. All right? Now, things get interesting when we draw things in, parametric equations are way more general. We can get graphs that we couldn't do before. Graphs, we can represent graphs that are not necessarily the graphs of functions. So it doesn't matter if a vertical line crosses the line in more than 2 places. We can represent those types of graphs with parametric equations. So here's one case. So imagine that we wanted to explore this parametric equation. This is example 2. We wanted to explore the parametric equations x equals 4 cosine 2 pi t and y equals 4 sine 2 pi times t, where t ranges between 0 and 1. See, this would be one that is hard now to eliminate the parameter, because to eliminate the parameter you would need to solve for t here, right? We can actually do it using inverse sine or inverse cosine, but it won't be a pretty expression. All right. So what happens here? Well, so this 4 cosine 2 pi t, maybe this would be instructive. I can see, I'm going to show you a picture in just a moment, a better one. But see, here's what the x is doing, and here's what the y is doing. So this would be the one for x, and this would be the one for y. So what x is doing between 0 and 1 is doing a piece of the cosine. So it's going like this, one iteration of cosine, right? Because it multiplies times 2 pi. So this is at 0, and this is right here at 1. And the one for y goes like sine, and it goes all the way from 4 to -4. So the amplitude is 4 because we multiply by 4. The one for y is similar, but now it follows along with sine. So it goes like this. All right. So now imagine if you put these two together. So what's happening? This represents the x, and this represents the y. Okay. And now I'm going to show you. So I'll try to do it here. You know, draw the picture of that shape. And what is it? So the x starts at 4, and at that time the y is 0. So we start somewhere over here. Now the x is becoming smaller all the way to 0, and at the same time the y is growing all the way to 4. So the x is smaller, so I go this way, and the y grows, so I go high. So it kind of goes like this, right? And then it continues. So it's sort of a shape like this. Now, I have a better way of drawing it. That's what I wanted to show you before we finish for today. So let me just show it to you in Mathematica. So you appreciate that it really is the expression that we want. So you can look in here. I put exactly what we want. So 4 cosine 2 pi t as my x coordinate, and 4 sine 2 pi t as my y coordinate. And what I asked for Mathematica is that only to draw it from 0 to u. And then I have a slider here for the u, so that you can see what happens as time goes by, right? Remember, this is kind of like a movie. That's the way we should do it, right? So as time goes by, it starts from 0 or close to 0, and then it starts growing and growing and growing. And this is what happens when we're at 0.25, right? And then I keep going. This is what happens when it's 1/2. And then I keep going, and this is 3/2. And then after 1, we end up right where we started. And it looks like a circle. It is a circle. Let me put it, let's make it just go like that. You know, keep going like that, right? So you can see how it really is a movie, right? So it starts at 0, and as the parameter goes, the range of the parameter increases all the way to 1, we keep drawing the curve, like you can see here, right? We draw the curve, going along, right? T is increasing. You can see the T over here, right? I mean, I called it U, but it's the same thing. How it goes from 0 to 1, and when we do that, we actually seem to be drawing a circle. So next class, what we're gonna do right at the beginning is to show that this is indeed a circle. So you can see the picture, it kind of looks like a circle, but we wanna make sure that it is precisely a circle. All right, so I'm gonna stop right here. Are there any questions, really quick questions before we stop the session? When is the test? And Gerardo raised his hand. So the test is whenever we had scheduled it. I don't have the schedule right in front of me. But yeah, someone said April 9th, and I believe that's correct. So we still have a little ways to go, but I wanted to let you know how we were going to do it. Gerardo, what's up?
Just a quick question. Is this
Yes.
when we start talking about vectors?
Yes.
So we're going to talk about...
We will start talking about vectors soon, yes.
Okay, but is it in this chapter? Just wondering.
I think it's probably next chapter. We have... No, it is in this chapter, actually. So we'll... let's see. Let me check quickly. It's next chapter. It's chapter 13. So we still have a couple of chapters, right? So no vectors yet. This chapter 12 is we will have parametric equations and polar equations and polar graphs.
Okay. Oh, thank you.
You're welcome. Anyone else? Okay, so we'll continue tomorrow. Stay safe, guys.